Semicrystalline polymers contain ordered crystalline lamellae dispersed within an amorphous matrix. This two-phase morphology gives them a useful combination of stiffness, strength, toughness, and processability. Common examples include polyethylene, PE, polypropylene, PP, polyoxymethylene, POM, polyethylene terephthalate, PET, and polyamides. Their mechanical response is fundamentally different from that of fully amorphous polymers because crystalline lamellae function as physical crosslinks within the molecular network. The amorphous phase provides molecular mobility and accommodates deformation, while crystalline domains provide rigidity and transmit load. Consequently, mechanical behavior depends not only on crystallinity, but also on molecular weight, chain entanglement, lamellar thickness, interlamellar spacing, crystallization history, and the connectivity between crystalline domains. Deformation mechanisms. At small strains, deformation occurs primarily through stretching and rearrangement of chains in the amorphous regions and deformation of interlamellar tie molecules. Tie molecules are polymer chains that pass through the amorphous phase and connect two or more crystallites. They are critical for transferring stress throughout the semicrystalline network. With increasing strain, several mechanisms can operate simultaneously: deformation and shear of the amorphous phase, crystallographic slip within lamellae, lamellar rotation, fragmentation, and reorganization, cavitation and microvoid formation, necking and plastic flow, and molecular orientation and strain hardening. At large strains, lamellae can reorganize into highly oriented fibrillar structures. This structural transformation is responsible for the pronounced strain hardening observed in many ductile semicrystalline polymers. In situ small-angle X-ray scattering, SAXS, or wide-angle X-ray scattering, WAXS, studies of PE have demonstrated that crystal slip and cavitation are strongly coupled and depend on temperature and lamellar morphology. Cavitation can produce strain whitening, while subsequent lamellar reorientation and molecular alignment contribute to strain hardening. Low Tg semicrystalline polymers. Why can they be brittle? Low Tg semicrystalline polymers represent a particularly interesting case. PE, for example, has a Tg near -125 degrees Celsius. At room temperature, its amorphous phase is therefore well above Tg and possesses considerable molecular mobility. Nevertheless, PE can exhibit either highly ductile or relatively brittle behavior depending on molecular architecture and morphology. This apparent contradiction arises because low Tg alone does not guarantee macroscopic ductility. For a semicrystalline polymer to undergo extensive plastic deformation, stress must be effectively transferred between neighboring crystallites. Tie molecules provide this connectivity. If their population or effectiveness is insufficient, deformation becomes localized near crystal/amorphous interfaces. Cavitation, interlamellar separation, crack initiation, and catastrophic fracture can then occur before stable plastic flow develops. Thus, a low Tg provides molecular mobility, whereas sufficient intercrystalline connectivity converts that mobility into macroscopic ductility. This distinction is essential for understanding the brittle to ductile transition, BDT, in semicrystalline polymers. Role of tie molecules. The density of effective tie molecules generally increases with molecular weight because longer chains have a greater probability of connecting neighboring crystallites. Molecular weight distribution is also important because a relatively small population of very high molecular weight chains can contribute disproportionately to intercrystalline connectivity. The probability of tie molecule formation also depends on the distance between crystallites. Shorter interlamellar spacing increases the probability that a chain can bridge adjacent crystalline domains. Consequently, molecular weight, crystallization conditions, branching, and comonomer content can all influence ductility through their effects on morphology and tie molecule connectivity. Studies of narrowly distributed PE have shown that a relatively sharp BDT occurs with increasing molecular weight. Importantly, the critical molecular weight is not universal. It depends on crystallinity and crystallization history. Scientists demonstrated that the molecular weight requirement for ductility varies substantially with the semicrystalline morphology rather than corresponding to a single universal tie molecule fraction. Effect of crystallinity and lamellar thickness. Increasing crystallinity generally increases modulus, yield strength, hardness, and dimensional stability because crystalline domains act as rigid reinforcing structures. However, excessive crystallinity can reduce the amount of deformable amorphous material and alter the distribution of tie molecules. Lamellar thickness is also critical. Thermal history determines crystal thickness and interlamellar spacing. Slow cooling generally produces thicker and more developed crystals, whereas rapid quenching produces a finer morphology. Synchrotron scattering studies have shown that PE with different crystal thicknesses can exhibit substantially different cavitation and crystal shear behavior. More recent work has identified an important relationship between crystal thickness and the critical tie molecule fraction required for ductility. In both PE and hydrogenated polynorbornene, HPN, polymers containing thinner crystals required a higher effective tie molecule fraction to maintain ductility. This behavior was attributed partly to a greater loss of tie molecules during deformation. Therefore, the important parameter is not simply the absolute amount of tie molecules, but their effective retention and connectivity during deformation. Molecular weight, branching, and thermal history. Molecular architecture provides an effective means of controlling mechanical behavior. Higher molecular weight generally increases tie molecule density and chain entanglement, improving toughness and resistance to brittle fracture. However, excessively high molecular weight can increase melt viscosity and reduce processability. Branching changes crystallinity, lamellar dimensions, and chain connectivity. Short chain branching in PE, for example, can disrupt crystallization and modify interlamellar spacing. Carefully controlled branching can therefore balance stiffness, ductility, and processability. Thermal history strongly affects morphology. Two samples having identical chemical composition and molecular weight can display very different mechanical properties after different cooling or annealing histories. Crystallization temperature and cooling rate determine lamellar thickness, crystallinity, and interlamellar connectivity. These effects explain why processing conditions are as important as chemical composition when designing semicrystalline polymers. Cavitation and strain. Hardening. Cavitation is the formation of microscopic voids during tensile deformation, usually within or near amorphous interlamellar regions. Void formation can produce visible strain whitening and can either accommodate deformation or accelerate failure depending on the surrounding molecular network. During continued deformation, crystalline lamellae can slip, rotate, fragment, and become highly oriented. The resulting fibrillar structure supports increasing loads and produces strain hardening. Recent positron annihilation lifetime spectroscopy (PALS) studies have provided molecular-level evidence that deformation of polymers, such as PP, involves changes in free volume and development of highly anisotropic cavities. These observations connect nanoscale free volume evolution with macroscopic stress-strain behavior. Brittle versus ductile behavior. The balance between molecular mobility, crystalline morphology, and intercrystalline connectivity governs the brittle or ductile response of a semicrystalline polymer. In a ductile material, sufficiently long chains, adequate tie molecules, and strong entanglement networks effectively transfer stress between crystalline lamellae, allowing stable yielding, neck propagation, lamellar slip, molecular orientation, and subsequent strain hardening. In contrast, when tie molecule connectivity is insufficient, deformation becomes highly localized at crystal amorphous interfaces, promoting cavitation, interlamellar separation, crack initiation, and rapid fracture at relatively low strain. Consequently, even a low Tg semicrystalline polymer can be brittle if its crystalline domains are inadequately connected. Conversely, appropriate molecular weight distribution, branching, crystallization history, and lamellar morphology can produce highly ductile behavior, despite substantial crystallinity. The brittle to ductile transition therefore reflects a competition between plastic yielding and fracture rather than Tg or crystallinity alone. Time-dependent behavior. Because the amorphous phase remains mobile above Tg, semicrystalline polymers exhibit significant creep and stress relaxation. Under constant stress, molecular rearrangement produces time-dependent strain, while under constant strain, stress gradually decreases. Long-term mechanical performance is particularly sensitive to tie molecule connectivity. Slow crack growth in PE, for example, is strongly influenced by molecular weight, crystallinity, lamellar morphology, and intercrystalline tie molecules. These relationships are important for pipes, films, containers, and other applications requiring long-term durability. Materials design perspective. The mechanical performance of semicrystalline polymers can be tailored through several complementary approaches: increasing molecular weight or introducing a high molecular weight fraction, optimizing molecular weight distribution, controlling branching and comonomer content, adjusting crystallization temperature and cooling rate, controlling lamellar thickness and interlamellar spacing, introducing amorphous segments that improve molecular connectivity, and minimizing molecular weight degradation during mechanical recycling. These strategies illustrate a central principle of semicrystalline polymer science. Mechanical performance depends on the architecture and connectivity of the crystalline amorphous network, not simply on crystallinity or Tg. In conclusion, semicrystalline polymers derive their mechanical properties from the cooperative behavior of crystalline lamellae, amorphous regions, chain entanglements, and tie molecules. Low Tg polymers, such as PE, demonstrate particularly well that molecular mobility does not automatically result in ductility. Effective stress transfer through tie molecules and preservation of intercrystalline connectivity during deformation are essential for stable yielding, neck propagation, and strain hardening. Molecular weight, branching, crystallinity, lamellar thickness, thermal history, and processing conditions therefore provide powerful tools for controlling the brittle to ductile transition. Modern SAXS/WAXS, PALS, microscopy, and molecular simulations are increasingly revealing how nanoscale free volume evolution and lamellar reorganization translate into macroscopic mechanical behavior. These insights provide a foundation for designing semicrystalline polymers that simultaneously achieve high strength, toughness, processability, and durability.